We're going to look at two problems in this video, and both of them are word problems. And so what we want to have as a key takeaway from this video is recognizing words that would point us in the direction of linear or exponential. So our directions on the slide tell us to decide if we should use linear or exponential and then to write an equation. So as I read this, I have a patient, and prior to her IV being started, she had an intake of 720 milliliters. Once her IV was started, she was not to have anything orally. Her IV was started at 150 milliliters per hour. We're to model the total intake for this patient. So I'm really going to focus on the numbers that are in the problem and what are the words surrounding them. So first sentence, I see prior. So I see this before her IV, she is at this level of intake. And so really this is the starting amount. And we saw both our linear and exponential equations require us to have the starting amount. So that doesn't tell me whether it's linear or exponential, but it is a number I'll need to use. Then I have her IV, and her IV is running at 150 milliliters per hour. And so that means every single hour she gets exactly 150 milliliters. So as I look at this, I see this as a constant rate of change. And a constant rate of change means that this is indeed linear. So I should be writing a linear equation. In our notes, we have that linear equations follow the format y equals mx plus b. We noted that m is the rate of change. So I'll abbreviate that, the rate of change, the rock there, and b is the start. So the word problem gave me both of those numbers, and I get to plug them in. Y is equal to 150x plus 720. And I can double check this in my thinking. So if her IV ran for 2 hours, I would take 2 hours times 150, so that would be 300, and I would add it to the 720, and at that moment in time, she would have received 1,020 milliliters as her total intake. So my equation does seem to make sense when I pick a point and test it. Now, we do see this word here, model, and in an algebra context, that model is to create an equation. That works for the scenario. And we tested ours, our equation does work for the scenario, and so that is our answer or model. Our next word problem. It says in pediatric patients, given a 50 milligram per kilogram IV dose of Rocephin, it is found that the body will metabolize 14% of the Rocephin each hour. Your 32 kilogram patient was given a dose of 1,600 milligrams of Rocephin. Model the amount remaining in his bloodstream. So there's more numbers in this problem than the last one. I really have to decipher if those numbers are valuable or if those are distractors. As I read through it, the 50 milligrams per kilogram and the 32 kilograms, well, that would allow me to calculate the correct dose for this patient. And so if I set that up, cancel, I can take on my calculator 50 times 32, and guess what? That does equal the 1,600 milligrams that was ordered. So we didn't have to do that, but that's how the 50 and the 32 are used. So this amount I understood to be the starting amount, and that's because that was the dose. And so it's asking me amount in his bloodstream, and since it's given as an IV, that would have been put directly into his bloodstream, and so that is this amount that's in his bloodstream at the beginning. Then I go back here to the beginning. It said it is found that the body will metabolize, and so I understand that as to eliminate, to get rid of 14%. And so because this is a percent, I am working with a constant percent change. And whenever we have constant percent change, we have something that is exponential. So I decide this is exponential. And then my notes tell me my formula for that is y equals p 1 plus r to the t power. In that formula, I know that p is the start, and I know that r is the percent as a decimal. And so I'm going to fill in the values that I have been given in this word problem. So y is equal to 1,600, that's the starting amount, 1 plus, and then we had talked about in our notes that the percentage could be positive or negative. My understanding of metabolize is that the body is going to eliminate that. And so because it is leaving the body, I am going to put that as a negative. Now I do have to change the percent to a decimal. So we did that with our algebraic word problems. So 14 divided by 100 is 0.14. And so I'll subtract 0.14. And then I have my exponent of t, which is to be a variable. So on my calculator, I will do the math inside the parentheses to clean up this equation a little bit. So 1,600, and then I have 0.86 to the t power is my exponential formula. And you can see that this is called exponential because as opposed to y equals mx plus b, this formula contains an exponent. So that is how we approach word problems. We are looking in word problems for whether or not it gives us a constant percent or a constant rate of change. So rate of change goes with linear, percent goes with exponential. And so we are really just looking for those keywords in a word problem to help us set up our equation.